Hi everyone, my name is Ryder Sabale and my project was on global air pollution. The project's dataset had 23,463 records and 12 variables, which include the AQI values and categories of each gas and pollutant observed, as well as overall AQI value and categories. The gases here are carbon monoxide, ozone, nitrogen dioxide, and PM2.5. PM2.5 stands for particulate matter, specifically particulate matter with a diameter of less than 2.5 micrometers. For reference for how small that is, a human hair is 20 to 200 micrometers thick, so those particles are super fine, can't really see them, but they're still there. The Air Quality Index, or AQI, indicates how polluted an area's air is. The higher the score, the more harmful the air quality. This is an overview of my data, but during data preprocessing, I got rid of around 200-ish records because of missing values and duplicate records. The goals of this project are to be able to predict a city's AQI value from its component AQI values through machine learning, and to hopefully discover any trends between cities and countries from their respective AQI values and their relative locations to one another. The questions that I wanted to answer during this project were what greenhouse gas or pollutant is most indicative of a city's AQI value, which countries had the highest or lowest average AQI values, whether there was a correlation between a country's location and their average AQI value, what percentage of measured countries were living with unhealthy air according to their AQI measurements, and how did variance of AQI values within a country relate to that country's average air quality level. For question 1, I took the numeric variables from my dataset, I created a correlation matrix, and then generated a heat map from that matrix. I chose to use only the numeric variables instead of also the categorical ones because those categorical values were derived from the numeric ones and were cluttering the data. It made it hard to see, and only the numerical data was showing the same thing. So I only use that. From this heat map, if you look at the first column or the first row, you can see all of the correlations from AQI to its component values, and you can see that PM2.5 is by far the strongest correlation, having correlation 0.98, almost 1. This suggests that PM2.5 is the most abundant pollutant in the atmosphere, and more importantly, it implies that it is the greenhouse gas or pollutant that is most indicative of a city's AQI value. Here's a better look at the heat map if you had trouble seeing it. As you can see, PM2.5 is way more correlated than all the others. For question 2, I took the initial data set, grouped it by country, and took the mean AQI value for each country. From this, I got the countries with the highest and lowest AQI value. However, deriving an overall trend from this data without any complementary data like economic data or I guess data that shows like what they burn, what they use, kind of is out of the scope of this project. But from a glance, you can see that like more advanced, more industrialized countries tend to have higher AQI values, especially those that have high access to oil, and countries that are somewhat smaller, not really as industrialized, especially island nations, tend to have lower AQIs. Here's a better visualization or a better look at those visualizations. For question 3, I took the average country AQI data that I had used for question 2 and put it into Plotly to create a map visualization. Initially, I had wanted to plot the individual cities into a heat map through geospatial data, like from GeoPy, but when I tried to get that data, I was getting timed out by the API because I was trying to get way more than 1 a second. So if you do the math, 1 second for every city, 23,000 cities, that's 6.5 hours to get all of the data, which was way more time than I had allotted to make this visualization and analysis. But from this map, we can still see that countries with higher AQIs do tend to be near one another. However, any conclusions I can make, like what causes this, are not as close. So there is a correlation, but what causes this, I can't say. Here's a better look at the map. For question 4, it was a lot more simple. I took the average country AQI data again and made a function to map it to the AQI category according to the AQI index. Then I generated a bar chart and took percentages from that and put it into a pie chart. So Most of the countries were good or moderate, so they had okay, but 16.7% of countries did live in either unhealthy for sensitive groups or unhealthy levels of air quality. To be more specific, unhealthy for sensitive groups means that only people with pre-existing conditions would be harmed by the air quality, but unhealthy means that like a significant portion of the general population is harmed by the air quality. Here's a better look at the visualizations. Note that the colors do reflect the AQI colors, the index. Lastly, for question 5, I calculated the standard deviation of AQI values for each country. Then I removed the countries with only one record or with a standard deviation of 0 because they wouldn't be useful here. And then I plotted them against their average AQI for each country to see if there was a relationship between AQI and standard deviation. As you can see, there's not really a correlation between AQI variance and average AQI value. A lot of these values are near 0, but they're not 0, so they still ended up on the plot. But as you can see, even ignoring that bottom row of values, it doesn't really show any correlation. They're just kind of scattered around. For machine learning models, I was choosing from 3 models: regression, support vector machines, and k-nearest neighbors. However, as we had established that the categorical data was a derivative of the numerical data, I was leaning towards regression. Additionally, the correlation heat map from question 1 suggested that less features would be more important in determining AQI value, so I went with regression. The categorical prediction from a support vector machine, or SVM, or k-nearest neighbors model could be derived from the numeric predictions of my regression models. As for the machine learning pipelines, I first pre-processed the data by gathering only the numeric data. The component AQI values were used as the data, and the overall AQI value was used as a target. I then split that data and target into sets of 80-20 training testing splits. After that, I fitted the models to the data before adjusting any of the hyperparameters just to get a baseline of where to start from performance metrics. As for what they were, I chose mean absolute error, mean squared error, and R2 score. Mean absolute error and mean squared error were used to show the variance in the data, and the R2 score was to show how well the model approximated the actual data. That being said, mean absolute error was kind of there just to make sure I wasn't like overfitting. Finally, the models were cross-validated each time with a hyperparameter. Each time a hyperparameter was changed through grid search CV, and by that time I had the fitted model. Starting with lasso regression, lasso regression uses L1 regression, and after putting it through my pipeline, I got a mean absolute error of 4.569. I got a mean squared error of 79.634, and I got an R2 score of 0.974. R2 score is from 0 to 1. Closer to 1 means you approximated the model better, so having a score of 0.974 is absolutely amazing. Here we can see the correlation coefficients, or so we can see the coefficients from the lasso model, and they are somewhat similar to our correlation coefficients, as PM 2.5 is way above the rest. Surprisingly enough, though, ozone also has a non-insignificant correlation coefficient, so that was surprising. For the elastic net regression model, which uses L1 and L2 regularization, I got a mean absolute error of 4.534, I got a mean squared error of 79.528, and I got an R2 score of 0.974. Again, the R2 score here, being the exact same, was fantastic. If we look at the coefficients found by the elastic regression, we can see that, like the lasso coefficients, they also reinforce what we saw in the correlation heat map. But notice here how some of the coefficients are actually 0. This is the difference between L1 and L2, given that L1 is the square instead of absolute value of the coefficients, or they're determined by the square or absolute value of the coefficients. L2 can actually get to 0. For the ridge regression model, which only uses L2 regularization, I got a mean absolute error of 4.568. I got a mean squared error of 79.632. And again, I got an R2 squared score of 0.974. Again, this is basically the same R2 score, which is, again, amazing. If we look at the coefficients once more, we can see that it also reinforces the correlation heat map. And from these results, it seems that regression was absolutely the right model given how well it was able to model the data and predict AQI value. So I'm very much happy with my choice of ML model. As for the challenges and insights I've encountered during this project, my biggest challenge has been the limited scope of my data. The data available was only on like air quality matrix, so any meaningful conclusions had to be drawn in concussion with other knowledge like locational data and other information about the cities and countries which I didn't have at the time. This ties in with my main insight I learned, which was the importance of scalability. The dataset used in this project was large, which was great for the initial analysis and modeling, but it made it a nightmare to add more data. For example, the GeoPy API limit made it practically impossible for me to add geospatial data to my analysis. And given the large nature of my dataset, the breadth of cities and countries made it practically impossible to add informational analysis to my project, given I would have to go through either 20,000 cities or 200 countries to sift through data. Overall, my model was successful in accurately predicting AQI data, and most of my questions either resulted in straight answers or meaningful trends to continue analysis. So I'm happy and I guess pleased. That being said, thank you for listening, and are there any questions?